Okay, well, let's get started with what's going to happen this week, next week, in the very near future to kind of help you guys plan some things out. This week is going to be a little unusual because tomorrow and Thursday are the English 1 and 2 STAR exams. So if you are not taking those, you guys get late start days. You don't have to show up until 1:35, and I've got the schedule right up here on the board. So they'll probably be ringing the bell about 1:30 to let you know to go to class. 1:35 is when the tardy bell is going to be. Now, they're all 30 minutes except for second period, which has 5 extra minutes for announcements because that's kind of built in there. But what we're going to be doing, we're starting with conics today. We're going to get as far as we can. Basically, today's an information day. We won't actually get to a real problem until Wednesday. Tomorrow, when I see you folks, we'll have a binomial theorem exit ticket. 30 minutes should be plenty of time to get it done and turned in before you leave. Wednesday, we'll continue with parabolas, talking about conics, but something else is due that day. Okay, the homework. Okay, so the binomial theorem homework. In fact, if you're just picking up the homework today, there are a few extra copies over here. Make sure you get with somebody and ask them about the powers on 13 and 14 and make sure you have those correct. Okay, because I talked about that on Friday. Thursday, I will not see you because that's going to be a 5 through 8 afternoon. And then on Friday, we continue the notes, but I don't know how much further we're going to be able to get because we have our first quiz on Friday. That's going to be over arithmetic and geometric series, the homework that we just turned in on Friday. Okay, so that's what's happening this week. Next week is going to be a short week because we don't come what day? We don't come Friday the 19th. Now, this Friday is a normal school day. It's next Friday. It's Good Friday because it's right before Easter. So we only come to school Monday through Thursday next week. And Thursday is going to be our first exam, okay, right before the long weekend. So looked at to cover probably binomial theorem as well as whatever conics sections we're able to get through up to that point. Okay, so that's what's happening in the next couple of weeks. And when you think about it, we're down, including this week, 7 weeks left of the 2018-19 school year, and then we are done. So seniors, we got 7 weeks, less than 7 weeks before you walk across the stage. So that's going to be an exciting time. Any questions? Zach? Thursday, I will not see you, and Friday, we got a quiz, and we'll get as far as we can on the notes. Jack. They're about 30 minutes each. Here's the schedule right up on the board. Okay. Okay. Any other questions? Okay. All right, well, let's go ahead and get started, and we'll see how far we get. So what is a parabola? It is the set of all points in a plane that are equidistant, equal distance, from a fixed line that we call the directrix. So it's the word direct with RIX at the end of it, okay? And the focal point, a point not on the line. The focal point, or you can call it the focus. Okay, either or. There's going to be a lot of interchangeable vocabulary today. All right. So the intersection of a plane and a double napped cone. So right now you're not really understanding what that's referring to. You may remember early on one of the questions in the district assessment was talking about intersecting a double napped cone with a two-dimensional plane. What kind of figure you would get. Hopefully this makes a little more sense as we talk through it. But think about one cone. In the conics section, we refer to that as a nap, N-A-P-P-E. So if I take two cones, two of those naps, and I place them vertex to vertex, that's the double nap diagram that I'm referring to. So I'll show you that in just a minute. But intersecting that diagram with a two-dimensional plane is what gives me these graphs. We'll first start with a parabola. Then we'll move on to circles, then ellipses, and finally hyperbolas. Okay. So this is one of 3 last, bless you, major units that we'll have for this school year. After conics, we need to talk about parametric equations and then see how far we can get with polar coordinates. We'll see how that works out. However, when the plane intersects with a vertex, a degenerate conic will appear. Now, in just a moment, I'll go ahead and show you a video that'll visually show you how this happens. Algebraically, there are a lot of different reasons why you might end up with a degenerate conic. First and foremost, you'll probably be dividing by 0, which would make it undefined, which is why you're going to get a degenerate. But you have 3 different types. You either have a single point, you have a straight line, or you have intersecting lines. Okay. So each of those results from a degenerate conic. A degenerate circle or a degenerate ellipse is a single point. A degenerate parabola is a straight line. And a degenerate hyperbola is going to be a pair of intersecting lines. Okay, so right now, the vocabulary probably doesn't make a whole lot of sense. Let me go ahead and show you, has everybody got it copied? Okay, let me show you the double nap diagram first. This is on your second page here. So when you go ahead and put one cone point to point, this is what we refer to right here, that's the vertex. Okay, and every double nap cone is going to have an axis of symmetry that runs straight down the middle of it. So if you take a two-dimensional plane and you start to intersect one or both of these naps in a PPE, remember that's what we're referring to as a cone, that's where you get the different graphs that we're going to be looking at. So I know it's kind of hard for me to just stand up here and talk about it. Let me show you this right here. Okay, hopefully this works.
Sections. In this module, you will learn about conic sections. When a straight line intersects a vertical line at a fixed point and rotates about that fixed point, the surface obtained is called a double right circular cone. A double right circular cone consists of 2 cones joined at a fixed point called the vertex. The line that rotates about the vertex is called the generator, and the line that remains fixed is called the axis. A right circular cone has a circular base, and its axis is always perpendicular line from the center of the base to the vertex. The perimeter of the base is called the directrix. The lateral surface of a right circular cone is called a nap. A double right circular cone has 2 naps. The nap above the vertex is called the upper nap, and that below the vertex is called the lower nap.
Man, I could really go for a nap right now. You know somebody was thinking. Okay, back to the video.
Also, the angle between the generator and the axis is called the vertex angle. Conic sections. If a plane intersects a double right circular cone, we get 2-dimensional curves of different types. These curves are called conic sections. Depending on the angle made by the plane with the vertical axis of the cone, the plane can cut the cone in 3 different ways. Ellipse. When the plane intersects the double right circular cone in such a way that the angle between the plane and the axis is greater than the vertex angle, we get a closed curve called an ellipse. When the plane is perpendicular to the axis, the ellipse becomes a circle. Thus, a circle is a special type of ellipse. Parabola. When the angle made by the plane to the vertical axis is exactly equal to the vertex angle, we get an open curve called a parabola at the intersecting surface of the cone. Hyperbola. The plane intersects only one nap of the double right circular cone as long as the angle between the plane and the vertical axis is greater than or equal to the vertex angle. However, if the plane intersects the vertical axis at an angle smaller than the vertex angle, the plane intersects both the naps of the cone.
And that's what a hyperbola is. It looks like a symmetrical set of parabolas. They're going to be opening away from each other every single time. But what we're going to learn today about parabolas, how they're constructed, that type of construction does not apply to these here. So they're not really parabolas. When we get to hyperbolas, we're going to refer to those as branchings. They have their own specific way of being constructed. Okay.
To form an open curve called a hyperbola, which has two disjoint curves, degenerate conics. If the plane intersects the double right circular cone at its vertex, the ellipse becomes a point.
And see, that right there, that's what we refer to as a degenerate circle or a degenerate ellipse. If the plane intersects the vertex but does not intersect either of the naps, that's when a degenerate graph is going to be formed. So if it only hits the vertex here, that's a single point in space. That's a degenerate circle or a degenerate ellipse. Now imagine, they're going to show it in just a second. Let's say that the plane is rotated so that it just rests on the surface of the cone, the surface of the nap. So think about that curved surface and you put a flat 2D surface right on top of it. What would be the intersection between the curved surface and the two-dimensional plane? Okay, so what kind of graph would it form? Remember, what was one of the other three that we listed a moment ago? We had a single point. Okay, you're close. It's going to be a straight line. The intersection between the surface of the nap and a two-dimensional surface is going to be a straight line. So if it goes through the vertex but just rests on the nap itself, that's a degenerate parabola. Sorry, degenerate parabola. There, right there.
The parabola becomes a line, and the hyperbola becomes two intersecting lines.
And you'll see in this case right here, you get the two intersecting lines when that axis of symmetry through the double nap is in the two-dimensional plane. Okay, so these are your three degenerate cases. A single point, that's a degenerate ellipse or a circle. One single line, that's a degenerate parabola. Or two intersecting lines, that's a degenerate hyperbola.
Figures so obtained are called degenerate conics. In this module, you have learned that when a plane intersects a double right circular cone, two-dimensional curves called conic sections are formed. There are three types of conic sections: ellipse, parabola, and hyperbola.
And the reason here it's only saying there are three is because circles are very much related to an ellipse. Think back to geometry. Is a square a rectangle? Yes, but a rectangle is not a square. So you have a very similar relationship here. A circle is an ellipse, but an ellipse is not a circle. So a circle is a special type of ellipse.
When the double right circular cone is cut by the plane so that the angle between the plane and the axis is greater than the vertex angle, the ellipse is obtained. When the plane is perpendicular to the axis, the ellipse changes into a circle. If a double right circular cone is cut by a plane so that the angle between the plane and the axis is equal to the vertex angle, the parabola is formed. If a double right circular cone is cut by a plane so that the angle between the plane and the axis is less than the vertex angle, the hyperbola is formed. If a plane intersects the double right circular cone at its vertex, the figures formed are called
degenerate conics. cut off at the last part for some reason. Okay. So now, let's go back over here. So hopefully, does that kind of help you to visualize what those definitions are telling you? Always makes it a lot easier when you see it than, when you're just trying to describe it. Okay, so I'm going to go through the rest of the vocabulary here, and then we'll start talking about the actual diagram. So a directrix is a fixed line that is plus or minus p units from the vertex. The value p, the directed distance from the vertex to the focus of the parabola, is called the focal length. In fact, when you're talking about the distances contained within a parabola, it's all based on one variable, p. The only three distances you'll ever have within a parabola are going to be p units, 2p units, or 4p units. Okay. A line segment that passes through the focus and has endpoints on the parabola is the focal width. It can also be referred to as the focal chord. Okay, but when I was in school, a lot of resources kind of refer to it as another name. I'm always going to refer to it as this. The latus rectum. Okay, I am very proud of you guys. Very good. Normally when I say that, people start to snicker. You said rectum. Only first period today started to giggle when I said that. Second and third period, obviously, we have a much higher sense of humor. Okay. We definitely turn the other cheek. Okay. I'd go ahead and make another joke, but it'd probably be pretty crappy. Yeah, okay. All right. All right. Anyways, we refer to it as the latus rectum, and I'll tell you what that means in just a second. It is parallel to the directrix. Now, the absolute value of 4p is the length of the chord through the focus and is perpendicular to the axis. Okay, so let's go ahead and put all this together and start talking about how it's actually created. Now, you remember from way back in algebra, every parabola has a line going straight through the middle of it that we call the AOS. Remember, that's the axis of symmetry, right? That's this right here. Now, where the axis of symmetry and the parabola touch, that's your what? Starts with a V. That's the vertex, okay. So that's my vertex right here. Now, the two items that are responsible for making the parabola look the way it does is the focal point and the directrix. The focal point is always contained within the parabola. So F right there, that represents my focal point. This dashed line right here is the directrix. Okay. Now, the parabola and the directrix will never intersect. In fact, the parabola always opens away from the directrix. Okay, no matter what direction he opens. So the definition that we were looking at just a moment ago, all the points in the plane that are equal distance from these two items, that's what a parabola is. So let's say anywhere on this parabola, I want to choose just some random coordinate, just some XY ordered pair. If I take that ordered pair, if I connect it to my focal point, and I connect it perpendicular to the directrix, that's going to form congruent segments. That's what the definition is referring to. Okay. Just connect some ordered pair on the parabola to both the focal point and perpendicular to the directrix. Now, I can do this again. Let's say I choose another random ordered pair up here. If I connect that point to my focal point and then perpendicular down to the directrix, I'm not saying that all four of these are going to be congruent. I'm just saying that the two created from that point, those will be congruent to each other. Okay. All right. So how many times could I do this? I can do this an infinite number of times. For any point that I go ahead and put on the parabola, I can connect any of them to the focal point and then perpendicular to the directrix. I've always got two congruent segments. That's how parabolas are actually constructed. So the vertex is a point on the parabola. So this distance here to the focal point and then down perpendicular to the directrix, those would be congruent to each other as well. In fact, that is what we call the focal length. from the vertex to the focal point, that's the focal length, and that's where you get your value of P. The distance from a vertex to a focal point is P units. From a vertex to a directrix, that is P units. Now, I should say perpendicular to the directrix. That's where you find P units. Okay. Now, let me go ahead and remove these two distances right here. All right. Because now I want to go ahead and show you what the lattice rectum is going to be. This is a line segment that goes through the focal point, stops on the parabola. It's always parallel to the directrix. So this segment right here, parallel to the directrix, it goes through the focal point and stops at the parabola. That right there is what we're going to refer to as the lattice rectum. Really, all it does is tell me the width of the parabola at the focal point. Okay. Beyond that, really doesn't do a whole lot. Okay. Now, these endpoints right here, we're going to refer to those as EPLRs. EPLR, EPLR. Now, if the parabola opens up or down, the left EPLR is what we're going to call what? The right is what we're going to call EPLR2 if it opens up or down. Okay. Right, Ethan? Right. So what do you think EPLR stands for? Endpoints of the lattice rectum. That's exactly right. Endpoints of the lattice rectum. So you need 3 points in order to get a graph of a parabola. So typically I like to have people find the vertex and the 2 EPLRs. Okay. So I said there were 2 other distances here, 2P and 4P. The distance from a focal point to either EPLR is always 2P. So the full distance, the length of the lattice rectum from one endpoint to the other, that's where you find 4P units. Okay. So see, if you know what the value of P is, you can easily navigate through the parabola and find anything you need. Okay, it's all based on that one distance. And it doesn't matter what direction the parabola is opening. This parabola was opening up. Let's look at a parabola that opens sideways. How about right? Okay. So this right here would be the vertex. The parabola always opens away from the directrix, and the focal point is always contained within the parabola. Okay. So how far is it from a vertex to a focal point? That's P units. From the vertex perpendicular to the directrix, that's P as well. Now, what do we call the line segment parallel to the directrix that goes through the focal point and stops at the parabola? Remember, that's the lattice rectum. Okay, so this point is an EPLR. This point is an EPLR. Which EPLR is 1? The top one, there you go. So the bottom would be 2. So that way, if I go ahead and give you that information, say on a quiz or a test, you'll know exactly which one I'm referring to, how the parabola is going to be oriented. If it opens up or down, EPLR 1 will be on the left. You go left to right. If it opens left to right, then you go top to bottom. Okay. How far is it from a focal point to an EPLR? It's always 2P units. So 2P, 2P. So the full length of that lattice rectum, 4P. Okay. So in here, we may have to limit ourselves to only these 4 directions, up, down, left, and right. Is it possible for a parabola to open diagonally? Yes, absolutely. If we have time, I would really like to show you those. They're what we call rotations. They're not difficult to work with, but it, again, just comes down to time. Really, we've got 6 weeks when you think about it, because the last week is pretty much review and finals. Okay, and we may or may not have to take a district assessment again. I hope not. We'll kind of see how that plays out. But any questions so far on the diagram? Okay. Now, let me go back to this guy right here. Now, typically, your vertex is going to be referred to as HK. The vertex is going to be referred to as HK. H is your X value, K is your Y value that you're going to see in the equation. What I want to go ahead and do is find the coordinates of all the other points using the distances we were just looking at. Okay, so here's the focal point. Let me go ahead and get the EPLRs back in here. So EPLR, that's the first. EPLR, that's the second. Okay, this is the directrix. And remember, the directrix is a line, so we have to give the equation of a line. Okay, so from the vertex to the focal point, remember, was P. Vertex perpendicular to the directrix was P. Focal point to an EPLR is 2P. And then the full length of the lattice rectum was 4P, right? Okay. Well, here's the thing. When you're moving inside these parabolas, because we're not dealing with rotations, you're only going to be going one of four directions. You're either going to be going up, down, left, or right. If you're going up or right, you're going to be adding the values. If you're going left or down, you're going to be subtracting them. Okay. So which value do you think I'm going to affect if I'm moving vertically? H or K? It's going to be K. If I'm moving horizontally, then H is going to be affected. So let's take a look at the focal point. I'm at the vertex that I'm calling HK. I want to go from this point up P units. So because I'm moving vertically, K is the one that's going to be affected. So the coordinate of the focal point should be H, K plus P. Okay. See, the focal point and the vertex are on the same vertical line. That's why the H doesn't change. I didn't move horizontally. I only moved vertically. Now let's say I want to go from a focal point to an EPLR. What's going to be changing, H or K plus P? H, because now I'm moving horizontally. What's nice about this is that no matter what these coordinates of the EPLRs turn out to be, I know that the Y value, that K plus P, is not going to be changing. Okay. In fact, what's the distance I'm going to go from the focal point to that EPLR2? It is a distance of 2P, so what would I put here? Where did I start? I started at H. So this would be H plus 2P. So what would it be if I went left to get to EPLR1? H minus 2P. Okay. And now let's finish up this directrix. Now sometimes it helps people to go ahead and think about the ordered pair. If I started at the vertex and went up, remember it was K plus P? So if I start at the vertex and go down, then it would be H K minus P, right? But remember, the directrix is not a point, it's a line that goes through that point. So the actual equation you need is Y equals K minus P. Now, first period took me up on this. Second period did not. Do we want to go ahead and draw a parabola opening in a different direction and do this as well? Would anybody like to? We feel confident? Okay. Then I already showed you this. Thanks to the video, we kind of have a better idea now where these graphs are going to come from. We have the double nap diagram, and we go ahead and start slicing one or both using a two-dimensional plane. Now, one thing we're going to get to pretty quick, the conic sections can be defined algebraically as the graphs of second degree or quadratic equations in two variables. Okay, so this is our general form, where A, B, and C are not all zero. We'll get to those later in the week. Did anybody have the opportunity over the weekend to look over completing the square or watch the video? Because definitely this week we're going to get to our first example where we're going to be given an equation that looks like this, and we're going to have to rewrite it into the standard form of a parabola. So we're going to have to remember completing the square. If you do look at the website, I put some notes on there for completing the square, and there's also a video I recorded of myself kind of walking you through that process. Okay, so it is there if you need some refresher. All right, so the next couple of slides are just copying some information. The first column represents if the parabola is at the origin, vertex 0, 0. And the second column represents if it's not at the origin. The vertex is at some point that we're calling HK. All right, so I'll give you a little bit of time to copy that down. there anybody out there who still needed the key and did not get it from Friday? Okay. Okay, now think about the three distances we have in a parabola. Does anything look familiar in the equations for a parabola? What's the one of the three distances we see in the equation? 4p. There you go. 4p. So in the equation, if it's written correctly, you're always going to know what the full length of the lattice rectum is. Okay, there's just one catch. That 4p coefficient has to be in front of the non-squared term or group. If the coefficient is ever placed in front of the squared term or group, you have to divide it over. Until then, it's not the correct value. So if you do know what the value of 4p is, well, how would I figure out the distance p? Yeah, just divide by 4. It's going to be really straightforward. Okay. Now, if x is squared, that's when you have two choices. It's either going to open up or down, because you'll notice here x is directly squared. Here x belongs to a group that's squared. If x is squared, it opens up or down. It's that coefficient that's going to help you decide what direction it goes. If it's a positive 4p, it opens up. If it's a negative 4p, it's going to open down. Okay. Is everybody done jotting the information down? Okay. So if a parabola opens up or down, it can also open left or right. And you'll notice, what's the major change in the equation? Okay. We still have h and k, but what variable is squared now? The y is squared. Okay. That's a key difference. If x is squared, it can only open up or down. If y is squared, it can only open left or right. And then 4p, whether positive or negative, will help you decide which one. So I'll give you a minute or two to jot that down. Okay, now key idea, whether x is squared or y is squared, the equation is only written correctly if that 4p coefficient is in front of the non-squared group. Okay. If it's in front of the squared group or term, then we have to divide it over. So you always want to look at that first because it's real easy to kind of go past it. Is everybody done copying this down? Okay. So let's take a look at some equations. Let's say I have these four right here. So what I want you to do is on each one of these, you're going to tell me what the vertex is, what direction it opens, and then you're going to help me figure out what the value, the distance P is. Okay. So let's take a look at this first one. X minus 5 squared is equal to 8 times y plus 2. First off, is it written correctly? Is that coefficient in the right spot? Yeah, the coefficient has to go in front of the group with no square. Okay, the only thing that's allowed in front of the square is a positive 1. So this guy's written correctly. Now, be careful. Sometimes x is going to be on the left side. Sometimes y is on the right. You can switch those. You can even have the squared on the right or the squared on the left. Okay, you can switch those around, no problem. But h is always with x. K is always with y. And it's actually really similar to when you were writing the point slope form of an equation. For those values, to write the equation or to take the vertex, you have to take the opposite of those values. So for this first one, the vertex would be at positive 5, negative 2. Okay. Can anybody tell me what direction this equation would open, this parabola? First off, would it be either up, down, or left, right? Now, how do we know it's up, down? Okay, x is squared, so it has to be up or down. So to make the decision, look at your coefficient. Is it positive or negative? Because it's positive with x squared, the side would open up. Okay. So in fact, what is the length of the lattice rectum? What is 4p? It is 8. It's the coefficient of that non-squared group. So I know the distance from the vertex to the focal point, for example, would be 2 units. And sometimes it's going to work out very nicely for you. Okay. You might have some good whole numbers. Not always the case. Let's take a look at this one. Negative 8x squared equals y plus 3. First off, is it written correctly? It is not. The coefficient's in the wrong place. The only thing that's allowed to go in front of the square is a positive 1. So first thing, I'd have to write them correctly. I have to say x squared is equal to, now if I divide by negative 8, I'm going to have a negative 1/8 times y plus 3. So let me erase this up here. Okay. Now, is it either up, down, or left, right? Okay. So why are you saying down specifically? Okay, so x is squared, which means up, down, but the negative tells me it's going to go down. Perfect. What's the vertex? 0. This is the same as x minus 0 quantity squared. Okay, and then negative 3. Now in this case, 4p would equal 1/8. Okay. When we go ahead and set up the equation to find p, we don't include a negative. That negative simply tells me what direction it's going to open. P is always going to be a positive distance, so that's why we just take the absolute value. So in fact, what would the value of p look like here? This is 1 over 32. If I divide 1/8 by 4. So see, sometimes those distances are going to be based on fractional values and not whole numbers. So sometimes they'll be nice and sometimes maybe not so nice. Okay. Let's take a look at this one. X minus 7 equals y plus 1 squared. Okay. So let's see if we can just get straight to it. Up, down, left, or right? Are there any that we can immediately throw out? It's definitely not up and down. Why? This is the first one. This is y squared. So it has to be left or right. In fact, can anybody tell me what is 4p? 1. Okay, now in front of the squared group, you're only allowed a positive 1. The coefficient 4p that we're looking for can only go in front of the non-squared term, the non-squared group. So in this case, yeah, 4p is equal to 1. Now because he's positive, this guy would open right. Okay. If x is squared, it's up or down. Y is squared, it's left or right. And you choose the sign of 4p to help me figure out which one. What would the vertex be? 7, negative 1. Now, if 4p is equal to 1, then that tells me the distance from a vertex to a focal point would be 1/4. So again, another fractional value, but definitely much nicer than the 1/32. Okay. And let's try this last one here. Y plus 4 squared equals -12 times x plus 1. First off, is it written correctly? Is the coefficient in the right spot? Yes, the only thing I'm allowed in front of the squared group is a +1. Any other value has to go in front of the non-square. So this is written correctly. Let's see here. For what? Up, down, left, or right? What direction would that parabola open? It would open left. Okay, I know y is squared, but 4p is negative. Okay. Let's see. Raphael, can you tell me the vertex? -1, -4. Very good. Now, why did he put the -1 first and the -4 second? Why didn't he go -4, -1? There you go. You always got to be careful as to what side of the equation x is on. Here, x was over here. That value always has to go first. Okay. In this case, I'm going to say 4p equals 12. Remember, I'm not going to worry about the negative. The negative, if I have one, just tells me direction. So in this case, what's the distance from a vertex to a focal point? 3. What in that particular graph, what would the distance from a focal point to an EPLR be? 6. Remember, that's always 2p. And then 4p would be 12, so that's the length. Is this starting to make sense? Okay. All right. Well, on Wednesday, we will continue this, but that is as far as the other classes got. Okay. Very good. Okay. So let's